All right, well, good afternoon. My name is Scott Young. I'm with Bastech. I'm the engineering manager there. I was asked to come out today and talk a little bit about applications for the direct metal additive manufacturing. For those of you who are familiar with Bastech, we've been involved in additive manufacturing since 1994, doing design work, prototype, mold making, pattern making, show models, all different kinds of things using the additive manufacturing as well as subtractive. We've got a lot of experience early on in methods of doing metal printing. Unfortunately, a lot of those have gone by the wayside because of complexity in the operations. What we are doing today is getting back into the metals. We are doing a lot of work with UDRI, GE, Unison, getting back and defining where metals printing is going to take us in the near future. Driving new ideas in tooling and product development. Today, 3D printing has come a long way with materials, with methodologies. In the metals world, we are capable of printing in cobalt, chrome, titanium, stainless, and just a wide array of different materials that allow designers to really think about what they're doing and utilize the best material for their solution. With minimal post-processing, conformal composite design, as well as lightweight structures, we're opening up a whole new world to how we are doing things in the manufacturing world. If we take a look at the process, the DMLS process is really fairly simplistic and complex at the same time. We're working inside a heated chamber, laying a fine powder down over the bed and bringing a laser in to fuse all of the material together. Once the material is created into a part, we can take that off the build platform using a wire EDM process, and from that point we can utilize CNC machining, we can utilize traditional methods of polishing, machining into tolerance, anything that we have to do to finish the given part. Capabilities, again, we're going back to some materials here, and you've got a nice list of materials, anywhere from cobalt, chrome, different Inconels, different stainless steels, depending on what you're looking for. Again, we've got a wide range of dealing with motorsports, commercial products, aerospace, biomedical. It's really up to you what you want to use it for. We've got materials for you. Advantages that we've got right now is there's no binders. The powder is really fine. We're looking at powder that goes down to 5 microns, which is just a fraction of a human hair. So we're really, it's a fine powder that's laying down. That helps us get a high density part as well as fine surface finish. Looking at the precision and repeatability of these machines, we are able to build parts and repeat them over and over and over again, holding tolerances down to plus and minus 5 thousandths. A lot of castings can't even, hold that type of tolerance. So this is a good method. We can utilize machines that have multiple lasers so I can get the builds to come off faster. So production is a possibility now, as well as being able to work with complex shapes, contouring, product. Maybe I couldn't build it before because of the complexity of the dies, but now today I can do it in a DMLS process. One process, it builds, it's done, and I can move on with it. Conformal design, which is one of the things we're going to get into a little deeper later. The conformal design allows us to wrap cooling and heating channels around a part, giving us better thermal conductivity in the tooling. It gives us the capability of conforming product around tight areas. Maybe I need to create a manifold, but I'm in and around a lot of other components. I can still create that manifold, just it's going to be a very non-traditional looking component. getting into some of the applications and why we're doing what we're doing. If you take a look at machinery, special machines a lot of times have components that are very low volume, to say the least. We're talking 1, 5, 10 parts. And these products, I may still have to make dies for them. I may have to do different tooling processes to get them. Thank you.
Space, I'm sorry.
The advantage is I can define them. I can make them customized for my machine. I don't have to buy something off the shelf. I can make it very custom and still get low quality with high quality. Dental and healthcare, you can imagine this is all very custom fitting type things. And, we'll get into this a little bit more later, but I can do a lot of different things, and again, I'm dealing with custom, low volume type applications. End use parts, this is one of the most common things that are coming out right now with machines that have up to 4 lasers in them and can actually build 4 parts at one given time or focus 4 lasers on one part to make it build faster. We can do a lot of different things fast. And that's where a lot of the end-use parts are going to come in. The repeatability, the tolerance that I can maintain, as well as making parts maybe not as fast as a stamping press is going to put them out, maybe not as fast as I can do in some methods, but for low volume, it's very economical. Tool making, again, this is another item we're going to get into a little more, but knowing that I can get better cooling, knowing that I can be more efficient in how I'm producing my tool, knowing that I can, eliminate some of my traditional processes helps me to provide tools faster, more economical to our customer at a really a reduced and overall cost, not just in the tooling, but with the production of especially injection molding. I'm going to have less scrap rate and other things of that nature. Cycle time is another one. Talking about the end-use parts, I've actually got a part up here today. We made this part fairly recently, and it's a really good example of what we can do with DMLS. This part gives you an idea of the surface quality that we can get off of DMLS. You can see on one side we've actually cut in so you can see inside, but you can also see the finish. And this was not, it has not had anything done to it other than we took it out, we cleaned it out, got all the passage clean, and then cut it so we could see what was going on inside. In this particular one, we had a defect that we actually caused in the post process. We needed to see what it was. But feel free to talk to me afterwards, and if you go over to the Bastech booth, which is in that direction, you can always stop by there. We have some of our DMLS parts over there that you can look at, feel, and see how they're actually lighter, stronger, things of that nature. We talk about the freedom of design, in conforming to other parts, fitting into different areas, fitting into tight circumstances. We can also do small holes. And in DMLS, it's very difficult to get small holes cleaned out. You're building in a powder bed, as you saw in one of the earlier slides. We're laying powder out. We're compacting it down in some cases and then bringing the laser in over top. Well, you can imagine a small 35 thousandths diameter hole running through a part. It's very difficult to clean out, but using vibratory tables, using heat technology, using air blowing in there, we can do things, get those areas clean. I've actually gone down to as low as I think it's a 25 thousandths diameter hole now. So a lot of different things that we're doing. If you look at this part again, I'm adding multiple components. This part actually has 6 tubes that are inside, and if I were to take and manufacture this in conventional methods, I would have to make a 2-piece housing so that I could take all of the tubing, put the tubing inside, fit it all together, and then put another housing on the outside. I have a risk for leak. I have a risk for all different kinds of scenarios, as you can imagine. By doing it in one piece, I can manufacture it, get it off the machine. This build time was actually fairly low. It took less than 10 hours to build. So it's well worth the cost of what we're doing. Talking a little bit about mold making, we are working with UDRI, GE, and other companies right now to figure out where we are going to go with the tooling aspect of metals additive manufacturing. And, you know, Bastech has a long history of injection molding. Both the owner, Ben, and I have been injection mold tool designers and makers for years. We know these tools fairly well, and when we start looking at cooling, this example is a really kind of a unique example. You can see I've got one part up here, and we'll have this back at the Bastech table that you can look at it better. But what we've done is actually make a clear SLA part so you can see what's going on inside, and we have a double helix in here that is allowing me to cool from the top and the bottom of the core at the same time. So I've got one water channel coming in, and you can see the blue. It comes in from the left, it goes up, it drops into a helix that comes from the bottom up, and then it also goes straight to the top and goes from the top down. The orange or red side is the collector side, and that is collecting it. So we actually have cooling going up and down all at the same time, giving us a much more even cooling method in this core. We can do the same thing in cavities. The other options that I have is around the helix. I've defined the cross section of the helix to be more of a cross shape, so I can help with turbulence and I can help with getting more surface contact on the cooling water. So as I'm running it up in, I can do different shapes. I can do elongated shapes. I'm not stuck with the traditional drill. I'm not stuck with the traditional baffle. Some of the places that we're going to look at this are not just in cooling, though. Really anywhere where I have to move thermal, liquids, airs, hydraulic. One of the things that I'm looking at, thermoplastic material flow. If you are into injection molding, some of the restrictions that we have a lot of times are simple hot runner manifolds. 3D printing can open up a whole new world in how we distribute that plastic into the different cavities. With what Bastech is doing over the next year, we're going to be taking a look at a lot of these issues and then doing more presentations to come out and show the public as to, you know, what we're coming up with, why we're doing different things, and how we want to help the tooling industry find better ways to utilize this DMLS process. If you've ever done fixtures and gauges before, a lot of times we'll take a fixture plate and lay it down, and we put a lot of aluminum or metal blocks building up, and then we CNC the tops of it. What if I can take and do simple pieces that I can lay down on their side and do physical structures, more of a webbing structure, minimize my material use, maximize what I'm doing with the component. I can bring it back up, set it up, do a quick finish machine on the top side of it. I've got my tight tolerance, I've got lightweight, and I've got minimal material use. These are all directions that we're looking at right now. This is another idea of how cavities and cores could change. You know, if you're familiar with injection molding, in this particular case, I have a cylindrical part that I'm molding, but what I'm actually doing is taking a 1-inch material piece all around the part. And once I have that 1-inch material thickness, I'm going in and putting conformal cooling inside. Again, I'm getting really close to my part area. I can have really close lines, and let's face it, while we've all wanted to, you've never been able to drill in that manner before. So this allows us a lot of different opportunities. I don't really want to go back to a flat square pocket again. I've got everything contoured around, but I can take some ribbing structure and just drop it down to my flat pockets. Just because I want a flat pocket, it's easier to mill, it's easier to get into the A plate and B plate. I don't have to fill it with steel. By running a simple web structure down, I've solidified everything that I need. I've got my strength, I've got my less material, it's lighter in weight, and I'm still getting the strength of steel. Good news is, miraging steel, I can go in and I can make the part, harden it, very similar to working with H13, and get up to 54 Rockwell out of it. So I'm getting good hard tool steel at the same time. If we want to look at doing things more like a progressive die or a forming die, again, I can do that primary shape. I can put the strength where I need it and then start webbing out areas that I don't need all of that. Again, making lighter weight, faster process for the DMLS, faster process, less material use. I start lowering my cost on the DMLS parts. In essence, some of the things that we are doing are really looking at rethinking design. If you look at everything that's going on, one of my last lines down here I really tend to like. A lot of people talk about getting rid of design for manufacturing. We're not getting rid of the design for manufacturing concept. We are simply adding in a different tool in the toolbox. And in reality, this is what we're doing. Instead of a CNC machine, we're buying a DMLS machine. Instead of setting things up in multiple different machines, I can do a lot of things right in one process. So we're looking at, if you understand the surface finish you're going to get out of your machine, if you understand the tolerance that you can get out of your machine, a lot of times you can actually reel in your tolerance just by building a part, seeing where you're at, and going back and saying, okay, now I'm going to dial this in and start running production and start making 4, 5, 10, 100 parts at a time in these machines. Understanding the material properties. We look at all of these things as designers, and then typically we go back and say, okay, well, I have to machine this. I have a 3-axis milling machine. This is what I have to design around. I have to let my tool shop make it. In this case, we can throw a lot of that out the window, utilize the technology, and it adds one of the greatest toolboxes right back into our tool shop. This is one of the optimizations, if you will, of utilizing DMLS. This particular part is just a wheel, if you will, or a impeller. But as these impellers grow in size, a lot of times I want to drop the weight. I need the strength. I need the strength of good metal, but I need to drop the weight. I can take a look and say, well, maybe my wall thickness, if I drop my wall thickness down to 40 thousandths of an inch, the steel is still going to give me the strength that I need to provide what this has to do for me, but I can hollow out the inside, supply it with a web for strength, and build the part. When I'm done with the part, all of my excess powder comes out the bottom. I drop my weight, I use less material, and using less material, I actually build a little bit faster. These are where we're looking at. Maximizing strength, minimizing weight. I promised people I wouldn't talk too long. I know that we got a little bit of a late start. One of the things that I wanted to do was to make sure that we had a little bit of time for questions and answers. Does anyone have a question? Yes. A lot depends. Now, if I look at this part, this is actually a very solid core. Okay, this part took roughly, I want to say 50, 55 hours, but it's a very tall part, and I specified I wanted it built standing up. Helps me hold concentricity and things of that nature. So in that case, it took a lot of time. To build this part, I was down in the 10, 12-hour range. Possibly even under that, I don't remember off the top of my head now. But, you know, a lot of the time goes back to the part itself. If I can build the part and lay it fairly flat, time's going to go fast. Really, we're looking at how many layers do I have to build the part in, and I have a certain amount of time for each layer because I have to drag the material over top, pack it down, get out of the way, let the laser do its job. Yes?
Maximum size capacity.
Pardon?
What's your maximum size capacity of this gun?
Right now, most of the DMLS machines will only go up to, certain ones go up to 10 by 10 by 13. Some of them are going up to 15 by 15. It depends on the manufacturer of the machine. If you take a look at some of the other metals options, they're more of a laying down weld options. Some of them will even go up to 200 inches long by 59 inches. So you can get some that are really large. The one we're going to be getting, should be getting it in any day now actually, is a 10 by 10 by 13. Yes?
When you lay the sand or whatever on it, once you run through the run, you can use the sand as once you use that pass.
Most definitely. That's one of the great advantages because even though I am done, pardon? Okay, I'm sorry. The question was, can you reuse the material that's being put in the bed? So we're putting material in the bed, we're using the laser on it. Once the build is done, we're taking the part out. What do we do with all this excess material? What do we do with the material that's coming out of the part? All of that is very easily used right back into the system. It goes through a filter, so we're not taking any clumps. We pull the clumps out, reutilize the material. Again, this is what allows us to keep our costs down. Yes? Layer thickness, I'd have to go back and look at it, but I want to say we're dealing with about 0.5 of a layer thickness, so it's fine. Keep in mind our powder is only, what, 2/10 of an inch? So we can lay down a fair amount of powder in that 0.5. Yes?
Sorry to come back to me again, but as far as the materials go, can you still bring it to a Class A surface finish?
Most definitely. If you can come up here and take a look at this. This is more of a B2 or B1 finish right now. But yeah, I can polish this. I can go right to a mirror finish if I wish. That's one of the niceties, especially using a machine that packs the material down. I can get a really good surface finish and really good density. If we take a look at, what kind of product I'm getting out at the end, these parts that are being, compacted, welded with a laser, I am getting parts that are equal to or surpassing the quality of high-end castings. So you can imagine right there, I'm not getting porosity in there. The question was, how do we know that we don't have porosity? Most of it is just taking a look at the part. We can x-ray parts, obviously, but in order to look at it really close, if I can get a Class A finish on it, I'm not going to have a lot of porosity in there at all. If I were getting porosity, I could not get that finish. Anyone else? Well, again, on behalf of Bastech, DRMA, and the AMTS show, thank you for coming out. We do appreciate it.